So we left off after having generated an equation using Newton's first law as applied to M1, mass M1, where we saw that the tension in the string acting on M1, which pulls up, is equal to the weight of M1 moving down or pulling down, which is why M1 remains at rest. Or we want it to, right? The thing is we want to calculate the value of M1 such that when we set up the real world scenario here, it is the weight force of M1 is going to offset the weight force of M2 plus the things dealing with the ramp. And when we did that for M1, we only had to deal with one direction of motion because there's only vertical, right? There's only forces in the vertical direction here. So we didn't have to do any vector decomposition or any of that, and we ended up with that equation there. The hard part of this kind of situation comes with the ramp and having to deal with the ramp, okay? So what forces were here? I know we started this yesterday, but let's just go ahead and continue from here. And let me just stress, if you can handle the analysis of this and what's going to follow after, which is, well, what if the system is accelerating and it's not at rest? It's not in static equilibrium. Then if you understand how to deal with both of those, you're like golden on forces. Okay? It doesn't get much more complicated. Anyway, so what forces were acting on this guy? We had the force of gravity, which I like labeling mg because that's what always ends up going into equations. And again, if you want to know why it's mg, wait for our unit on universal gravitation and circular motion. M2g, that's what I said. There's a 2 there. See? It's right there. And then what force? Tension. Which way does tension point? Parallel to the ramp and up in the direction of the string. So it's going to be something like that. Normal force, which points perpendicular. Good. And remember, we define coordinate axes such that our lives are easier. There's one coordinate system here that will minimize the amount of work I have to do. And remember, there's no physics without measurements. There's no measurements without coordinate systems. However, the choices of those coordinate systems excuse me, are arbitrary, okay? So I can pick any coordinate system. Some will require me to do a lot more work than others. If you're like me, you want to do the least amount of work as possible while maintaining, obviously, full understanding. But there's one particular coordinate system where I only have to decompose one vector. If I were to use the standard coordinate system here, then I would say, all right, well, the weight force, mg, is in the negative y direction. Don't have to decompose that. But the tension force would not be in either. The normal force would not be in either. So I would have to decompose both of those vectors, which means I got different angles going on, different triangles. Yes, they're going to be related because we got a 90-degree angle between them, but it makes my head hurt just thinking about trying to do that because I know it's unnecessary. I can make my life much easier and only have to do one vector decomposition by defining a coordinate system where the normal force and the tension force will be in line with my principal axes, my x and y axes. It doesn't matter if they're positive or negative, it's just they're aligned, then we don't have to do vector decomposition. So I define, let's do it here, down the ramp as the positive x direction and perpendicular to that as the positive y direction. Coordinate systems are arbitrary. I can use that one or the standard one, or one that doesn't make any sense, where it's like this is the positive x direction and this is the positive y direction, where nothing aligns. And I got to decompose all three of those vectors. And it would be a nightmare and it would be silly, but I'd get the same results. I'd get the same results. That's the beauty of physics. And another thing, the good thing about that is that I can pick the most convenient coordinate system, meaning the one that requires me to do the least amount of work, which is this one. Because then I only have one vector that doesn't align with my coordinate axis, so I only have to decompose one vector, and that is my weight force. You with me on that? All right. Now, decomposing a vector just means drawing a right triangle where the legs of the triangle are in line with my coordinate axis. So I always draw my vector components like this. I go in the y direction first, and then I make a right-hand turn, make a right turn, left turn, and there's my triangle. Okay, there's my components. The reason I do this triangle always is because I memorized long ago that the angle of elevation of the ramp is congruent to this angle here. If you remember your geometry, if you remember Mr. Butterbaugh and what he taught you, then you can prove to yourself that those angles are congruent. If you're like me and you don't remember how to do geometry proofs, you can probably look at it and kind of know that this is 90 degrees, and so this is 90 degrees, so this and that has to be complementary to that, so that must be, so you can kind of walk your way through that, why those angles need to be congruent. Or if you're really like me, you can just memorize it. These guys are congruent. Okay. It's not hard to, at least mentally, like actually writing down the proofs the way you're supposed to in geometry. I forget how to do that, but yeah, those are congruent. And that's important to know because this is the opposite component, so it's the sine component, m2g sine theta. This is the adjacent component to that angle, so that's m2g cosine theta. Notice when we were first learning about vector decomposition, some students said, can we just always make the x direction one the cosine component? Because for projectiles, it always is the cosine component. In this case, the x direction component is the sine component. So that's why I told you back then, don't pigeonhole your brain into that. X direction is always the cosine component, y direction is always the sine component. Don't do that. It's not always true. Think of it in terms of, is it opposite? If it's opposite, then it's the sine component. If it's adjacent, then it's the cosine component. What comes before the sine or the cosine? Whatever the actual vector happens to be. And the way I think about it, once I've gotten to this point, and I've got my vector components there, I don't even use this guy. I don't even worry about M2G, the actual vector. It doesn't align with my axes, so I don't use it. Right? I didn't when I was doing projectile motion, and these were velocity vectors, or displacement vectors. Excuse me. And so I don't need to do it here. I just use the components. Okay? All right, well, before we move on, let me point at something out. You picked up some notes on the way in. So these notes, yeah, if you look at, first of all, on the second page, ignore Newton's law of universal gravitation. We're going to do that in our unit on circular motion. But on the third page, after it describes the most commonly used forces that we deal with in this class, it has the box and it says steps for solving challenging force problems like the one we're solving now. First step. What is the first step there? Draw a free body diagram. Draw a free body diagram. That's all I heard. I couldn't hear you. And then establish your convenient coordinate system. Notice we did that here. Okay? And then write an equation relating the forces for each axis. For M1, we can only do one, because we only had forces acting in one of the axes, right? In the direction of one of the axes, positive or negative. Excuse me. Here we got both directions, x and y direction. So I can write an equation for both. Let's just do the y direction first. The net force on mass 2, so net force 2 in the y direction, so comma y, I know it has to be what? 0. Net force has to be 0. If it's not 0, what is the system doing? Not moving. It could be moving and still having the net force 0. If the system is moving and it has a net force of 0, what does it do? It continues moving at constant velocity. Very good. Thank you. All right. So remember, if the net force is 0, you don't want to say because it's not moving. You want to say because it's not accelerating. Okay. So the net force in the y direction has to be 0. And if I'm doing this the long way, I think of any time I expand a summation, right? That's the summation symbol, out into its constituents, the things that make it up. I think of like unpacking it and just listing all of the individual things. How many individual forces do I have in the y direction, positive or negative? In the y direction. 2. I have the normal force, and I have the y component of the weight force. Okay. The normal force is in the positive y direction, so I call that a positive force. M2g cosine theta is in the negative direction, so that's going to be minus M2g cosine theta. Don't let that sigma symbol, don't let that weird E throw it, don't let it make confused. It just means list all the forces in the y direction. If they're positive, they're positive. If they're negative, they're negative. That's just list them all. That's it. That's it. If they point this way, they're positive. If they point that way, they're negative. And those, the sum of those is 0. And I can add m2g cosine theta to both sides to get a nice little equation. The normal force equals m2g cosine theta. Now, it might have been this class, but I think it was second period. Does the normal force always equal mg? Was that this class? Okay, it wasn't.
Well, I asked if the normal force was equal to... Yeah.
It was, yeah, it was. Lee Taylor?
Yeah.
Lee Taylor. So if I have a mass sitting on the tabletop, then here the forces are mg and the normal force. If it's not accelerating, then the net force is 0. So the normal force magnitude must equal the magnitude of the weight force. Right? They have to be the same. So yes, the normal force is equal to the weight force if it's on a horizontal surface. As soon as you start putting an angle on it, the normal force, tell me, does it go down or does it go up when I start putting an angle? Lee, Taylor. When I start, if I go from here to where the normal force is m2g, but then I start putting an angle on it, what's happening to the normal force? It's going down. Because cosine of theta will never be bigger than what number? 1. And it's only 1 whenever theta is 0. Right? If you're in pre-cal, you should know this. You should kind of be knowing this. If you're not, then it's okay. You don't need to know this. But if you, in pre-cal, get this understanding, because it'll help you there. Yeah, cosine of any angle can't... If the cosine of an angle was bigger than 1, that would imply a right triangle with a hypotenuse shorter than one of its legs. That can't happen. So the cosine of an angle cannot be greater than 1. Okay? It's always going to be less than 1, except for that specific case when it's 0 degrees. When it's 0 degrees, the cosine of the angle is 1, and the normal force equals mg, right? The equation has that. The math has that built in. But then as soon as the angle starts getting bigger than 0, then cosine of the angle starts getting less than 1, and so we start reducing m2g until it's 90 degrees. What happens when theta is 90 degrees? What happens to the normal force? What's the cosine of 90 degrees, guys? If you're in pre-cal, you should know this. Straight up, cosine of pi over 2. Sebastian. Oh, disappointing. Huh? Haven't you had to memorize the unit circle at this point?
Yeah, it is. And then they forgot it.
The cosine.
But pi over 2?
That wasn't on the unit circle.
Cosine of pi over 2 is 0.
That wasn't on the unit circle.
It's straight up. It's straight up on the unit circle.
Yeah. So what's the x?
Pi over 2. The x is 0.
0.
The x is 0. Yeah. Hence why. Oh yeah, and you can look on the back of your formula sheet. It says the cosine of that is 0. Wait. Shh. But connect that. Listen. So it becomes 0. The cosine of the angle becomes 0. So the normal force becomes what? 0. What happens to an object that's on a surface whenever you put that surface 90 degrees? It's in free fall. There's no more normal force because it's no longer in contact with the surface. The math tells you the same thing that your brain does, your intuition, right? It's good stuff. Again, if you that last 3-4 minutes, if you're in Algebra 2, this is stuff you'll learn next year. For now, you just got to take my word for it and know that your calculator will do the right work. Right? All right. So here's another equation. Remember our goal. I know we got kind of sidetracked. Remember our goal is to find M1 such that the system will be in static equilibrium, meaning that the net force on this guy is 0 and the net force on that guy is 0. Right? With these two equations, can I calculate what that value of M2 should be? That value of M1 should be. Remember what I can measure. I have a scale here to measure my cart mass, and I have I have, I'm going to use my angle indicator, my level on my phone, because it seems to work better than this. We figured that out second period today. So I can measure the angle, and I can measure M2. And I need to calculate based on that what M1 is. Can I use these two equations to calculate that? Meaning M1 is my unknown, right? This is what I'm looking for. Can I use these two equations and the measurements that I am able to make? No. Because what else would I not know? Yeah. I don't know the tension. And I don't know the normal force. Although I could calculate what the normal force is, because I know all this stuff. I could calculate what it is. Is that going to help me, though? It's not going to help me. I need another equation involving tension. Can I get another equation involving tension? How can I get another equation? I can only get another equation from M2. So what do I have to do specifically in order to get an equation that has tension in it? Look at the x direction. Right? I need to analyze the forces in the x direction. If we're in static equilibrium, that implies that the net force in the y direction is 0, and the net force in the x direction is 0, and the net force in the z direction is 0, if we're doing three-dimensional stuff. Okay? It just means the net force is 0. An object at rest stays at rest in the absence of a net external force. So the net force in the y direction, the net force on mass 2 in the y direction, must equal 0. I know that if what I claim is to be true. Here, though, I'm going to skip the middle part, the whole unpacking thing. I'm going to go from that statement. First of all, it's not the y direction. And I don't know why you told me to write the y direction. Jeez.
Come on, pay attention, bro.
So the net force in the x direction, I can go straight. If I know that has to be 0, I can go straight. Just by looking at my free body diagram, I can go straight to the equation. What's the equation? Someone tell me.
T minus M2G.
Let's just look at the free body diagram. You're right. But I can look at the free body diagram and say what equation?
T equals M2G sine theta.
T equals M2G sine theta.
Let's go. Oh my gosh.
That is very easy as long as you've drawn your free body diagram, right? That is actually not a very difficult thing to do at all. Check this out. And I'm telling you, you guys that fight me on the free body diagrams, and when we did work on our next assignments, and you're like saying, Mr. Graham, I got the wrong answer. Can you tell me I did wrong? And I look at your paper, I see no free body diagram. I'm not even going to talk to you. I'm not even going to acknowledge your presence until I see a free body diagram.
I'll just wait for Isaac to get to the same question.
Okay.
You can take them out.
Also, you'll be shooting yourself in the foot for the AP exam because you're going to have to draw a free body
I can
diagram.
learn while I do.
Or you can just learn when you're
Yeah.
supposed to.
But that's
Excuse me.
yeah, exactly.
All right. What was I? Oh yeah. So really, all you need to do, draw your free body diagram, do your vector decomposition. Once you do your vector decomposition, forget about that vector, and just say, all right, if the net force is 0, I know the sum of all the positive arrows has to equal the sum of all the negative arrows. Sometimes there's more than just 4, but in this case, there's just 4. Great. But all I did to generate that, all I need to do to generate that equation is say all the up arrows equal all the down arrows. In this case, there's only 2. Right? They have to be the same. And for the same reason, all of the left arrows have to equal all the right arrows. Okay? I can go straight from the free body diagram to these 2 equations without having to think too hard. Like that's my deal. If it seems like I'm smart, it's just because I've been doing this so long. I struggled learning physics, but I wanted to learn it because I was interested in it. I struggled though. And this is how you can make it easier on yourself. Right? And you still get the same results. You can still do almost as good as people way smarter than you. Right. So there's hope, Lee Taylor. There's hope.
Yeah, maybe one day I can catch up to it.
All right, so what do I do to calculate M1? Do I have an equation that now, combined with the measurements I'm able to make, can I solve this problem now? Can I solve for M1?
Yeah.
If this is equation 1, 2, and 3, which equations do I need to use to solve for M1?
1 and 3.
1 and 3. Because they both involve tension. That's a system of 2 equations with 2 unknowns, M1 and T. Right? So if t equals m1g, I can just plug m1g in for that t. And I see that m1g equals m2g sine theta. Remember I told you, anytime you have an equation where every term has the same factor, we can just cross that factor out, right? So what does that tell me I can do here? Cross out the g. This has significance, guys. Pay attention. If you want to know physics intuitively, this has significance. The fact that g canceled out of the equation tells me that I can take the same setup to the moon and get the same exact result. And then I can take it to Jupiter, and if I can figure out a way to stand on Jupiter, I'll do the same experiment, I'll get the same result. Neptune, same thing. Okay? Why? Because the value of g doesn't matter. The value of g does not matter. How do I know it doesn't matter? Literally cancels out of the equation. If it cancels out of the equation, it has no bearing on the reality of the situation. Okay? There's significance there. Anytime something divides out completely that was there initially, that means that that thing has no bearing. Okay? One of the calculations that we'll do, what is the minimum speed that Isaac can take a corner with in his car before skidding out? Right? The solution to that problem, the mass of the car cancels out of the equation. Meaning that it doesn't matter if it's a little car or if it's a big F350 turbo diesel. Both of those cars are going to skid out at the same speed. Are there other factors involved? Yes, the type of tire, the material, the expense of how expensive your tires. Yes, there are some things, but in general, within plus or minus 5 or so miles per hour, the two vehicles are going to slide off at the same speed. Why? How can we explain that mathematically? In the equations, which we'll learn how to set up and solve, the masses of the objects completely cancel out of the equation, which tells you that the mass doesn't matter. Which is why they don't have different speed limits posted for a big F350 turbo diesel and a little smart car. Right? By the way, I know the smart cars are good for the environment, but don't drive a smart car, guys. You guys know what I'm talking about, right? You get in a wreck in one of those, you are not surviving. You're not surviving.
It's like a hamster wall.
No. Yeah. Where your head is like, the ceiling is here, and the window is here, and the back of the car is right here, right behind your head. Yeah. No. You hit a deer in a smart car, and you're probably going to die. Yes, hey, hold on.
You hit a butterfly. Speaking, if you have a plane going on the same turn, the same speed would be required.
Yes, but with a plane, you're going to have the center of balance, and you're going to have tipping to worry about. So there's other factors involved, but theoretically, yes. As long as you can neglect all other factors, yes. Consider a spherical plane. Yes. Okay. Oh man.
133.
I'm going off the side here. It's only until the end. Sorry people that are watching this after the fact, but whatever, you should have been here in school anyway. So look at our answer, it's easy. After all that work, I figure out that the value of M1 just needs to be whatever the value of M2 is, times the sine of our angle. That's it. That's our result. Notice if we plug numbers in way in the beginning, this is why big kids definitely do not. We are now firmly in the realm where we solve equations without plugging numbers in first. Okay? If you want to plug numbers in first, and you're going to fight me on that, you got 5 more weeks. 5 more weeks?
To what?
Till the end of the semester, and you can drop this class and go to pre-AP. Because that behavior will fly in pre-AP. In AP Physics 1, no. You can't not do it symbolically. Because we need intuition. We need an intuitive understanding of physics in this class. That's what my job is, to instill in you. And this little thing that happened here, very likely to miss it. Especially if you're the kind of student that doesn't want to solve symbolically first. You will miss that insight, right? Anytime that happens when you're dealing with equations, if you're plugging numbers in first, you lose that insight. You lose the fact that, oh, this quantity doesn't affect this quantity. How do I know that? Well, because it canceled out of the equation. Well, if you didn't deal with the equation like that, you're not going to see that happen. So make sure. Okay, let's make the measurements and actually do it. Again, this did not work second period. I'm going to go ahead and blame those students, though I did charge them with making the angle measurement. So we'll blame them.
Probably Ethan Anderson.
If probably Ethan Anderson, he's not very good at physics.
Yeah.
He sucks.
I know.
Oh, whoa. Watch your language, Isaac.
It's
Jeez.
just like we don't say we in pre-calculus. What if he hears this? He'll get revenge on you.
Okay. So I'm gonna go ahead and I'm gonna take this guy and put two of these masses. This is supposed to be 500 grams. Each of these is supposed to be 500 grams. But the manufacturers say 500 grams plus or minus 10 or so grams, right? Because manufacturing differences and stuff like that. So all together, and this is going to be M2, right? This is the mass that I'm going to put it here. M2 is going to be 1,482 grams. How many kilograms is that? Because we don't use grams.
Quite a lot.
1,482 grams. 1.482 kilograms. The angle. Again, second period, we used this angle indicator first, and let's just say that the system did not remain at rest. And that's always disappointing when that happens. Because physics is supposed to work.
Sounds like second period is worse for us.
Sounds like second period is probably the worst class I ever had.
Dang.
Good thing I'm not recording this, huh?
They have Giselle.
Wait, are we recording? Oh, uh-oh.
Oh.
I think we should
No, it's okay. We
my
can
awesome
remain
phone.
anonymous.
Okay.
iPhone 12. How's that?
Does anyone have a level that they can bring up real fast?
Yes, it shows you the incline like degrees, right?
Mine says 19 degrees. I have 19 degrees. Can someone else try and tell me what they get? 19 degrees. Okay.
I have a feeling 20.
Okay. So all I have to do is multiply that mass, which is 1.482 kilograms, times the sine of 19 degrees. Do I expect a number for M1 that's greater than or smaller than M2? Intuitively, what would you think? M1, does it need to be greater than or smaller than M2? The hanging mass here, does it need to be greater than or less than an M2? Less than? Greater than?
Yes.
The sine of an angle between 0 and 90 is at maximum what? 1. At minimum 0, and varies between those two. Right? So sine of the angle and any other angle between 0 and 90 is going to be some number less than 1. So you take M2 and you reduce it by some factor by multiplying it by that essentially ratio. So M1 should always be smaller. Yeah, and that should be kind of intuitive because you hang less mass here to offset this guy because this guy is also not just hanging there, right? He's on a ramp. And so the component of the weight that's fighting the motion this way is, again, a component of the weight. It's not the full weight. It's just a component of the weight. All right, and in your head, Lee Taylor, what is that?
At least 1.1. 1.1.
I think you're pretty far off there. It's 0.482.
You know what? I was close enough. I'm in radians.
0.482. What did you get when you were in radians?
You want to know?
Yeah. So the answer should be 0.482. What did you get on your calculator? 0.2211. Oh, that one you wouldn't know. Sometimes when you use the wrong unit, sometimes it's pretty obvious. Oh, I got a negative number for a mat? That doesn't make sense. I'm probably in radians. Get in the habit. This is one area where pre-cal students can actually suffer a little bit by being in AP1 and pre-cal, because when you're doing your trig units, you're always in radians, almost always in radians in your math class. In physics, we're almost always in degrees. So we do our unit on rotation, then we'll go into radians a little bit. Okay, 482 kilograms. Excuse me. So what I'm going to do Now, this guy has mass. Do I need to incorporate it in M1?
Yes.
Yeah. So I'm going to put that guy on the scale. It's rated at 50 grams. It's actually 50 grams. These guys obviously weren't each 500, right? Because there's a deficiency of 0.081 kilograms. What? 50 of me, yes. The world couldn't handle that. Barely handled one. What am I doing again? 482. So put a 200 on there. What's cool about these things, and you will be using these sometime in the future, the near future, you cannot move these and put them on different ones. I painstakingly took days a couple years ago putting these mass sets together. They are designed to have a specific number of each type so that you can go from 0 to 1 gram to 2 gram to 3 gram all the way up to 1.5 kilograms, 1,500 grams in increments of 1 gram. It's like an Olympic set of weights. You buy an Olympic set of weights and you can go up in increments of 2.5 or 5 pounds every time you move up in weight. Same thing. You take one of these and you remove it, that's destroyed. Okay, the whole algorithm, if you will, is destroyed. So never do that, or I'll get mad. Where are we getting? 482. Got little tiny ones that are 2 grams and 1 gram.
At 482.
Meet me at the bench.
482.
Okay, then.
All right. If this doesn't work, then I'm just gonna give up and go home.
I agree.
Okay.
End class.
Okay, so when I let go of it, and remember, if we're not right,
Uh-oh. Now we're on.
if we're not right, then the system accelerates. Even if it's a small acceleration, right? We start at rest, the system accelerates. Okay? If we are correct,
Wait, we are gonna.
then the system should not accelerate when I let go. And it actually worked.
We're good at this.
Yeah, we're better in second period. Second period, boo, second.
Boo.
What
Except
number did
Nolan.
they get?
I'm just kidding, second period.
Except Nolan. We love Nolan. We love Nolan.
Except Nolan.
What, how can we be better? How can we be
What
better?
number did they get?
Second period's way better
Yeah, no, but he used to be.
That's not good.
Okay, so not only, if the net force is 0, not only will a system remain at rest, but a system, if it was moving, would do what? Move at a constant speed. So let me give this guy a little bit of a nudge.
Dang.
That's pretty constant speed. It slows down a little bit.
I didn't believe that in 8th grade. It's hard. I didn't believe that in 8th grade.
Well, now you believe it, right? Look at that.
I do.
It's
Look
happening.
at that.
I still don't believe that.
Mr. Ehrlich didn't explain it that well.
Mr. Earth.
Yeah.
That's because even most physics teachers don't know physics. Not at this school, though. We got good physics teachers.
Really? Like who?
Except for me. Okay. So, good? What time is class end?
And like 9.
All right.
Like 11.
So what happens? What happens if I put some extra mass?
Acceleration will occur.
Acceleration will occur.
He messed up the algorithm.
Yeah.
Sure. Right. Okay.
It was perfectly fine.
So if you understand that, the rest of what we need to do, talking about accelerated motion, is almost the same. But if we know that the object is accelerating down if an object or a system of objects is accelerating, then if we have acceleration, what does that imply about the net force? It is not. What, Connor? What?
It is not zero.
No.
It is not 0.
This is like
Yeah.
less than
If by less than 0 you mean negative, yeah, that's fine. Because a negative force just indicates its direction.
Very true.
It's a good question.
Forces are
All right. One last thing, and we'll probably end a little early because
party
I think we're a little, no party. We end early and then I take a nap and you guys keep quiet so you don't wake me up.
Are we gonna have a party tomorrow? Because tomorrow we're about to go into a break.
I think we should.
So wait, so you're almost to the point where you can party all you want for about 9 days. Okay. So, one thing I want to point out, that very soon we'll learn how to, are we all listening? Everyone look. I can apply Newton's second law to this entire system. I can apply Newton's second law to the entire system at one time. Or I can apply, and I'll elaborate on this in the next few days. Your phones, Jalen. If you're not going to stay away for class, I don't want to see you awake on your phone. Okay. What was I saying? Yeah, we can apply Newton's first or second law to the entire system, but in this case it would be an entire system of two objects. Or we can apply, as we did in this case, Newton's laws to the individual members within the system. Okay, we're going to talk about that a little more tomorrow. One other thing I want to talk about, the coordinate system. So if I was to take my coordinate axes here and put them over here, I can actually relate the motions of the two individual objects to each other by noting something. Okay, if M2 is moving up the ramp at a constant 2 meters per second, describe M1's motion. 2 meters per second straight down. If this cart is accelerating down the ramp at 1 meter per second squared, what's this guy doing? Accelerating upwards at 1 meter per second squared. If this guy undergoes a displacement of -2 centimeters, this guy 2 centimeters downward, this guy experiences a displacement of 2 centimeters up the ramp, right? The motions are identical, right? The motion of this guy is identical to the motion of that guy, right? So I like thinking, what is it that's redirecting the forces? It's this pulley here, right? Now, do you guys remember learning about mechanical advantage and simple machines? Levers and pulleys and all that good stuff. So does a single pulley, let's see who remembers. There's people in second period that remember. So second period might be better than sixth period. We'll see now. Does a single pulley give you any mechanical advantage? Second period's better. Does a single pulley give you mechanical advantage? It does not.
I think it does.
A compound pulley system gives you mechanical advantage. That's when you have two or more pulleys and you have more contact points with the rope. Okay? If you have a compound pulley setup that gives you a 2-to-1 mechanical advantage, then you have to pull down on a rope with half the force. But you also get the object to lift up half the distance. So you got to exert that smaller force over double the distance, right? It's like pushing a crate up a very shallow inclined ramp, right? By the time you get it up to the top, it's going to be pretty easy to do. Lift that box up the same distance. You do the same amount of work, but you end up just having less force, okay? But a pulley doesn't let you do less force. A compound pulley does. All a single pulley does is redirect the force. And that can be helpful. If you had to get a box that's 150 pounds from the ground up to on top of this counter, you can lean down like this and you can pick it up like that and put it up here. I know probably a lot of people in here can squat 150 pounds easy, but it's easy to squat when the weight's here. It's much more difficult to squat when you actually have to lift something, right? So yeah, you try to lift with your legs, and that's what you do when you squat. And it's really easy to do with when you squat because of the way that the weight is positioned. But if I had to lift a box like that, I'm afraid to hurt my back, right? That's why they tell you lift with your legs. It's hard to lift with your legs when you got to be leaning over to pick something up. So what could I do? I could attach a pulley to the ceiling, throw a rope over it, and attach it to the box. What that means is that I got to use the same force. Again, a single pulley, no mechanical advantage. I have to use the same force that I'd have to exert when I lift it. But by putting a rope over a pulley, I've redirected the force, right? Instead of having to lift upwards on the box, I can exert a force downward on the rope, which will then, that direction gets transferred by the pulley to the box and lifts it up, right? When I do that, I can just lean back into the rope. So my weight actually combines with the force that I pull to make it easier to lift the box. Why am I saying that? Because the pulley in that scenario redirected the force. And so however fast I pulled the rope down is however fast the box rises. So when I think about the coordinate systems here, because I had a different one for each one, but I can kind of relate them if I just think about this positive x-axis for M2 just being curved around by the pulley, just like the rope. And then in that case, I would call this, technically, yes, the positive x direction, but I'm not going to write that. I'm just going to call that the positive direction for M1. And I know that that direction coincides with the positive direction for M2. Okay? So think of pulleys as redirecting not just forces, but also coordinate axes. And it makes a lot of this force analysis stuff pretty easy. You'll find when you start your understanding here, and the videos that we watch from Flipping Physics, start your understanding here, basic force problems involving one object become very, very easy. And then these more difficult problems where you have systems of objects connected by strings that are looped over pulleys, especially when we start throwing friction and maybe 3 objects into the mix, it can get kind of confusing. But if you understand this at the base level, drawing free body diagrams, going directly from those to your equations. Once we learn how to calculate acceleration by force analysis, then we can describe the subsequent motion, because that acceleration will be a kinematic variable, right? So we can describe subsequent motion of an object after being acted on by an external net force. And so that's where we're going with this. And that's all I have to say. Go away now.
Subscribe to the brand YouTube channel.